All right, so in section 1.2, let me just kind of go back and revisit that with you guys. Um, we um, we went through this introduction really quickly. Remember, we had this curve, and the idea was that we started off with the line PQ in red, and we were trying to see if we can find a tangent line. So what we started doing was we started getting the point Q, and we kept moving it closer and closer and closer to the point P along the curve. And the closer we got, the more tangent the line got, but not really tangent because it was still based on 2 points. So even down here, way at the green line, you can see it was still 2 points, right? We can keep trying to get closer and closer and closer, right? We could try to get the points as close as possible, right? But the problem is they still have to be two distinct points. So how is it possible for us to create a tangent line if we're given 2 points? Okay? So they were like, well, it's impossible. We can't do it. So we're just going to have to give up on that. And then they said, well, maybe we could. Now, they did create a secant slope from that problem, okay? So from that came a definition that you guys know as the difference quotient, okay? So this definition came out of section 1.2 where they said, well, at least we can figure out that the slope of a secant line is given by that equation right there. And they said, and then they started talking about limits, and as they discussed limits, they said, well, let's use this idea and let's try to figure out, is it possible for us to approach a distance of 0? And they said, well, that's not possible because when the distance is 0, that means the 2 points are the same, but they have to be two distinct points. And they said, well, what if we don't literally make the distance 0, but what if we just approach it? So we take a limit. Okay, would that be okay? So they thought about it and said, okay, let's try it. And from there, they were able to say, yeah, we could theorize a tangent line if the distance between the 2 points is infinitely small, right? As it approaches 0. So they created a new equation. And they said, we can take this limit as h approaches 0 of this secant slope. So the limit as h approaches 0 of f of x plus h minus f of x over h. So we had that, and they said now if we can put any type of function in here, we can actually figure out what its limit is going to be, and that's going to give us a slope for that function. Okay, the slope of that tangent line that theoretically would exist. Okay, so this is what they call the original definition of a derivative. Okay, so I'll just kind of write it down here. The original definition of the derivative okay, it's going to be f prime of x, and I'll write more about that in a bit, but we say that's f prime of x, that means you take a derivative of the original function, is the limit as h approaches 0 of f of x plus h minus f of x over h. Now, taking the derivative using this definition is a pain. It really is. It's not something that many people like to do because it takes a long time sometimes. We are going to learn a shortcut, but the reason why I don't just want to show you the shortcut and skip this part is because sometimes in the AP exams they want you to use the original definition to do a specific problem. So you do have to know what the definition is. So make sure you guys know that definition. Okay? So for us, we're going to use this definition to take derivatives of functions. Okay, so to give you an example, let me put example number 1 here. So the instructions are going to say find the slope of the graph of f of x. So find the slope of the graph of f of x equal to x squared plus 2x plus 1 at the point negative 3, 4. So finding the slope of the graph. So if I were to graph this thing and I go to the point negative 3, 4, there should be some kind of slope right there. And that's going to tell me the slope for the tangent line that's supposed to cross through that point. Okay? So right now we'll do the work, and I'll kind of show you a picture of it. We'll use Desmos just to kind of help us out a bit. But so we're going to take a derivative of f of x. Okay? When we take derivatives of anything, there's a lot of definitions. Calculus, we spend most of our time all year doing two things. Okay? Taking a derivative and then taking the antiderivative. So it's like I teach you for half a year how to tie your shoelaces, and then the other half year I teach you how to untie them. That's it. Okay, there's two main things we're doing in calculus all year. Okay, but the derivative, so the first half, doesn't just mean derivative. It means finding slopes. It means being able to find maximums and minimums to graphs, being able to find concavity of graphs, points of inflection, critical points, rates of change, related rates, optimizing things. Anytime you take a derivative, it has a ton of different meanings. So that's kind of like the hard part when you learn derivatives. The process of derivatives isn't terrible. Well, right now it is going to be, because you're not going to like this. I can almost promise you that. It's not that it's crazy, insanely difficult. It's just a lot of work. Okay, it's mostly algebra again, but it's just that you have to make sure that when you read a problem that they want you to do, you understand what they need from you. Not just take a derivative, but what does taking a derivative mean in this situation, right? And right now, sure, we're just going to take it. We're not too worried about it. But as we go into chapter, or later on into chapter 2, definitely into chapter 3, we're going to learn a lot more definitions of whenever they say do this, they mean take a derivative. So derivative also means this, maximizing, minimizing, all that other stuff, increasing, decreasing. So later on, the term derivative is going to mean a whole lot more. The process will still be the same. We're still going to just take derivatives normally, but just the meaning of it is going to be different depending on the problem. Okay, so that's going to be one of the things you have to try to put together as we keep going on. And then the same thing for integration. It can mean many different things. So anyway, let's get back to this. If I'm going to take the derivative, so I know f of x is equal to x squared plus 2x plus 1. If I take f prime of x, that's equal to the limit as h approaches 0. Now, f of x plus h, that means they want me to plug in x plus h into my f of x function. So, it's going to look like this. So, x plus h quantity squared plus 2 times x plus h plus 1 minus f of x. Well, f of x is x squared plus 2x plus 1. And all of that gets divided by h. Now what you're going to want to do at this point is you're going to have to expand the inside. So this is why I say a lot of people don't like this, because it just starts to kind of blow up sometimes. So I'm going to kind of start here. Let's write limit as h goes to 0. Now x plus h squared is x squared plus 2xh plus h squared. 2 times x plus h is 2x plus 2h plus 1 minus x squared minus 2x minus 1 all over h. So there you go. I expanded it, and now I'm able to cancel. Okay, I can try to cancel things out. the last term, so you see after the minus sign, I have x squared plus 2x plus 1. Those should all disappear eventually. The minus x squared minus 2x minus 1, they shouldn't be there anymore once I'm done simplifying. If they're still there, I did something wrong. If the 1 remains, something's off. If the minus 2x is still there, I got to double check my work, okay? Your f of x term should cancel stuff out with the previous term. So as you can see, I am able to get rid of x squared with minus x squared. I can get rid of a positive 2x with a negative 2x, and a positive 1 with a negative 1. So notice how these three terms that came from here are now gone. That's how you know you're on the right track. Okay? They should disappear. All right, so let's rewrite. Limit as h approaches 0 of 2xh plus h squared plus 2h, all that is divided by h. Now notice, I can try plugging in h equals 0 now, but what's my result going to be if I plug in my 0 right now? Well, 0 over 0, which is not, yeah. Well, it may not be D&E. We still have to wait to see what happens at the end. Yeah. 0 over 0 just means that it's an indeterminate form. We learned that in chapter 8, near the end of the square. We'll talk about that. But it's considered what's called an indeterminate form. Like I can't figure it out, right? Cannot be determined. So what I'm going to do is cancel out an h. Okay, you can see the h is on the bottom. I can get rid of one h from each term. So this h will go away. This will just become a 1. This one will go away, and that'll cancel. So now I have the limit as h approaches 0 of 2x plus h plus 2. Now I'll try plugging in 0 again. What do I get? 2x plus 2. That's my derivative. Okay, we call this the slope formula for f of x. So in other words, 2x plus 2 is how I can calculate the slope at any point on that parabola. If I want to know the slope when x equals 0, I plug it in, it's going to say 2. So if I graph that function, my slope at 0 should be 2. So let me show you this on Desmos, but let me just wait a little bit because I see some of you guys still writing things down. Actually, I know what I can do. I'll freeze the frame up here, and I'll go to Desmos. On the recording, you'll be able to see what I'm doing, but right now, for you guys, you'll just kind of keep writing that down. I'm just going to type out our function here. X squared, was it plus 2x plus 1? All right. So let me unfreeze the screen over here. And I'm going to take a screen cap of this. And I'm hoping that works. Why isn't that working? Entire screen. I didn't do it. Entire screen. It's not taking a screen capture. Oh well. Anyway, I thought I could do it from there. So, according to what we just found out, where does the slope equal 0 for this? At, well, not 1, at negative 1. Because notice that's the low point, right? So if you were to draw a tangent line at that point, wouldn't the tangent line be straight across? Right? You guys know what I'm talking about? So I was hoping, let me see if I can, I'm not sure why this is not doing this. See, draw a shape. So I'll just try doing this right now. But I'm waiting to see why it's not popping out. Supposed to have a program's supposed to open, but it's not opening, so I'm gonna have to figure that out later. But anyway, if I were to look at this graph, okay, you guys know that positive slopes obviously have a upward motion to it, right? It goes up this way. Negative slopes go down, right? Zero slopes are flat. So if I pretend this is my tangent line, as I keep approaching and approaching and approaching -1, you're going to see eventually this line that I draw at that point would be flat, right? And then as I keep going this way, it's going to start to kind of change. The tangency of that line is going to go like that. So the slope at -1 is 0. If I were to draw a line that's tangent to this point, it would be completely flat. Okay, a slope of 0. Now remember the formula that we just solved, 2x minus 2, or sorry, 2x plus 2? What would happen with 2x plus 2 if I plug in a -1? It becomes 0. It's telling me that at -1, your slope is 0. What's my slope when x equals 0? It would be 2, right? 2x plus 2, so if x is 0, that's 2. That means that if I were to draw an equation, a tangent line at 0, it would go from here and then 2 up, 1 over, so right here. So it would basically connect right across, having a slope of 2. If you wanted to figure out what the slope at 3 is, plug it into the formula. 2 times 3 is 6, plus 2 is 8. So any slope that you guys want, you can actually figure out now based on the formula that we just wrote down, which is 2x plus 2. So this derivative just gave you every possible slope, or the answer to every possible slope on the function x squared plus 2x plus 1. Okay, so now you can find any slope you want anywhere. Okay, so we used the original definition, which was the limit function, on the difference quotient, or the secant slope, to try to find the actual slope formula for this. Now, I'm not saying the y2 minus y1 slope formula, but the slope formula for this function. And every function has different ones, okay? X cubed has a slope formula of 3x squared. When you're doing these things, it's sometimes tedious to go through the whole process because you have to basically expand so many things and then cancel things out. But at the end, you're looking for a formula that's going to give you every possible slope. All you got to do is feed it a number, and it's going to spit out a slope for you, okay? So I know we have another one to do, but before we do that one, I mentioned to you guys f prime of x. Okay, so notation for derivatives. So there's a couple common derivative notations that you guys have to know. Okay, probably one of the most common is f prime of x. Okay, so f prime of x. That means to take a derivative of the function f with respect to x. Okay. Another very common derivative is y prime. So in other words, take the derivative of y. So anybody here a Transformers fan that's willing to admit it? I am, but if you're a Transformers fan, you know why they're called primes? Because they're all derivatives of each other. That's why they're called Optimus Prime, okay? So they're called primes because there was one before, and then there was a derivative of that one, and a derivative of that one. So you didn't know, but you were learning calculus while you were watching cartoons. So yeah, that's why they're called primes, because they're derivatives of each other. So they all share the same allspark, right? So it still has the same root function, but different changes as they move on. So There you go. So yeah, you've been doing math. You see, math can be cool, right? Look at Transformers. It's all math. All math. So y prime, another one that's very, very popular, and you're going to see me interchange. Sometimes I'm going to use y prime, sometimes f prime of x, sometimes I'll use dy dx. Okay, which means the derivative of y with respect to x, meaning I'm going to take a derivative, and the variables I'm taking derivatives of are x's. So the denominator tells you which letters you're taking derivatives of. Now there are two more, and these other two, one of them is kind of popular. The last one is like really not that popular. D dx, you'll hear me say that sometimes, d dx of a function. Okay, so this would be the derivative of f of x with respect to x. And then the one that you should never use, unless your teacher in a college tells you you must. I'm even going to change the color because I really don't want you to use it. It's that one right there. That means the same thing as the one above. The derivative of y, actually, the second one above. So derivative of y with respect to x. That's what this means. It just looks awkward. It's kind of like writing a 1 in front of an x. And not just x, but you write 1x. It's just, you're not wrong. It just looks wrong, right? So we don't really use that one that often. The dy dx is actually in honor of Isaac Newton. That was the notation he used when he said he invented the calculus. Leibniz, another mathematician, at the same time claims he invented the calculus. The problem was they were sharing notes together, but letters didn't travel as fast then as they do now. Now we send a text with a screenshot of something and say, look what I figured out, and in seconds you can say, wow, that was pretty good, you figured that out. As they were both figuring stuff out, they would snail mail each other, and when they would get it, they'd be like, oh, I already knew that. I discovered that 3 days ago. Well, this letter came like from 2 weeks ago, right? And then the other one would get the letters and like, yeah, I already figured that out too. So I guess I'm the one figuring everything out, and he's behind me, right? So Newton and Leibniz, they kind of had a bit of a beef, okay? Because they both claim that they discovered calculus, which I guess is kind of true. So to honor Newton, we use this notation here. To honor Leibniz, we start using his notation in chapter 4. So Leibniz will use this. Don't write this down yet because it's not going to mean anything right now. But what happens with him is this is his letter in cursive, right? His last name. So what they did is they just got rid of this, and we call that an integral. So this is integration or antiderivatives. So that's the notation they use for that, and that's in honor of him. So yeah, we do have feuding. You know, some people will claim it was Newton for sure. I mean, why wouldn't Newton discover it? The guy was a genius. But I mean, Leibniz was pretty smart too. So I mean, you got to be smart to do stuff like this when nobody else was doing it, right? So yeah, people will say it was one or the other. I guess it depends on who you respect more. So anyway, let me do one more example with you guys, and then that might be it. Because I'm not trying to rush through this. This stuff is not something that you kind of just want to go through and hope you get it. So if you guys have questions, just stop me. So example number 2. Find the derivative of f of x equal to x squared minus 2x. Now, by the way, when you're trying to decide which notation to use, you want to look to see what they gave you. So I gave you f of x. So I expect you, not that it's wrong if you don't, but I would probably expect you to use f prime of x. It just makes sense. If it's f of x, use f prime of x. If I would have given you y equal to x squared minus 2x, then I would probably expect you to use y prime or dy dx, because they're just kind of like, it just kind of follows that. You're using this letter, use a derivative notation that includes that letter, right? So for f of x, I would expect you to use f prime of x, or you could use ddx of the function, which would be ddx of f of x. So you'll see it as they start using it. And most of my students tend to just stick with f prime of x for the rest of their lives, and that's okay. You don't have to interchange. Some people prefer dy dx, and that's their best way of doing it. They just think that makes the most sense to them. To me, I go with what's given. So they gave me f of x. I will use f prime of x. Okay? And that's the limit as h approaches 0. Remember, that's where I'm just writing down definition again for us, okay? F of x plus h minus f of x over h. Okay? So let's go ahead and plug in our x plus h into our function and see what we get. So limit as h goes to 0 of x plus h squared minus 2 times x plus h minus f of x, which is x squared minus 2x. All that gets divided by h. Now go ahead and distribute and expand. So this is going to become limit as h approaches 0 of x squared plus 2xh plus h squared minus 2x minus 2h minus x squared plus 2x all over h. By the way, the shortcut x squared minus 2x, the derivative is 2x minus 2. That's the derivative, 2x minus 2. Okay, I'm basically using a general power rule to help us do that. You'll learn that in section 2.2, I think. So it's not like I'm going to keep you guys doing this forever. But you do have to know how to use this in case they ask you to do this on an actual AP exam. I will make you do this on one question on a quiz, okay? I'll ask you, take the derivative of this using the original definition. So I'm going to need to see all this work. By that time, you'll know the shortcut. So if, let's just say the function was x cubed, and you just write 3x squared, then I'm going to mark it wrong. Okay, I need to see the work. Okay, you got to put in the work because I got to see that you know how to use it. All right, but I only make you do it once because I know this is a pain. Okay, I don't like doing it that much either. I know shortcuts. Why do I want to do this? But it's something you guys need to make sure you know how to use. So let's cancel stuff out. X squared will cancel with negative x squared. Minus 2x will cancel with 2x. Again, I want you guys to notice that these two terms, I told you they're supposed to disappear, right? Notice they're right here, and I just canceled them out. If you have a negative x squared left over or a positive 2x left over, then you did something wrong. Okay, your distribution went wrong. Your expansion of x plus h squared went wrong. Something is wrong. So double check, because you should clear out that f of x function. So here we go. I got 2x h plus h squared minus 2h over h. Now cancel an h from each term. So this h is gone, this h is gone, this becomes a 1, this h goes away. So the limit as h goes to 0 of 2x minus 2. Actually, wait, no, I'm wrong. I forgot something. Plus h minus 2. I forgot the h. Yeah, it will go away on the next one. Now that I do direct substitution into it, it's going to become 2x minus 2. And this would be the slope formula for a parabola, x squared minus 2x. I can tell you the slope at any point. If you want to know the slope at 0, it's negative 2. If you want to know the slope at x equal to 10, it's 18. If you want to know the slope for the tangent line at x equal to negative 30, the slope for that tangent line would be negative 62. Okay, super, super steep line, okay, at that point. So now I could ask you any point, you should be able to find the slope at that point. Okay? So I am going to give you guys, this is the end, I'm going to stop here, but I'm going to give you one problem to try on your own. Now, it is a fraction. I'm kind of testing to see how well you guys know how to work with rational functions. And then we'll do it when we get back, okay? But this is an example for you guys. So this is your homework. One problem. Find the slope of the tangent line. So in other words, after you do the derivative, I want you to plug in the value to see what the slope is. Okay, the actual slope. For the function now notice this is f of t, not f of x. It still works just the same way, okay? So it's going to be f of t plus h minus f of t over h at the point 2 comma half. I'll give you the answer just so that you won't be like I don't know what the answer is. The answer is, let me see, so negative 1/4. Okay. So solution, the slope at that point, or actually to write it correctly, f prime at 2 is negative 1/4. In other words, the derivative when x equals 2, because that's the x value, is negative 1/4. So that's going to be your answer. Try it, see if you can get it. If you can, it's okay. We're going to work over this when we come back on Monday, but try to see if you can do that on your own. Okay?